sir.
Good morning. Am I audible?
Yeah, you're perfectly audible. I think
Thank
Trishani, you may carry ahead,
Yes,
please.
sir. Yes, sir. Good morning, one and all present here. I'm Trishani Acharji, and I would like to welcome everyone present here to the to the last day of IEEE 5th International Conference on Computational Intelligence and Networks, that is CINE 2022. Without any delay, I would like to call upon our keynote speaker, Dr. Sandeep Ghoshal, sir, and our keynote session chairs, Dr. Tanupriya Chaudhary, ma'am, from Senior Academician and Researcher, UPES Dehradun, Professor Niranjan Ray and Professor Monitipa Roy, ma'am, from our very own School of Computer Science Engineering.
Thank you, Trishani. The thing is that I'm Bengali, that is why the name is Tanupriya.
Sorry,
You
sir.
yeah, okay, thank you.
Extremely
Welcome,
sorry,
Sandeep
sir.
sir and all. Good morning, Sandeep sir. Good morning, Manidipa ma'am. Good morning, Niranjan sir and all presenters over here. I'm just giving a brief highlight of about Sandeep sir. Dr. Sandeep Ghoshal sir has received the BTech degree in Electronics and Communication Engineering from Kalyani Government Engineering College, Kalyani, India in 2012. He completed his ME degree in Microwave Communication in 2014 with silver medal for being the first ranker among the specializations in the Department of Electronics and Telecommunication Engineering from Indian Institute of Engineering Science Technology, Shibpur, India. During his master's, he was associated with a project work of retro directive communication sponsored by Space Application Center, ISRO. He obtained a PhD degree in the Department of Electronics and Electrical Communication Engineering, Indian Institute of Technology, Kharagpur, India in 2020 in the domain of computational electromagnetics. His research focus was based on the development of an electromagnetic understanding of mutual coupling among different transmitting and receiving nodes in the physical layer. During his PhD period, he has developed an integral equation-based computational electromagnetic simulator for the purpose of full-wave electromagnetic characterization. He also developed a eigenmode solver for computing the generalized eigen nodes and eigenvalues of a coupled system. He co-invented a new theory called theory of coupled characteristics modes for fast and efficient computations of any finite large array of antennas. A practical use case in massive MIMO communication or large telescope array technology. And the proposed theory is generic in terms of any antenna structure or design frequency of interest. Dr. Sandeep has been working in the core research and development team of Antenna Toolbox in MathWorks India Private Limited, India, since September 2019, where he is currently working as a senior software developer. He is a co-winner of the Startup India competition Ideathon by the Bengal Chamber of Commerce and Industry, BCCI, Kolkata, and West Bengal Electronics Industry Development Corporation Limited, WEBEL, in 2020. Dr. Sandeep has been recognized with the International Scientist Award 2020 on Engineering, Science and Management by VG Good Technology Factory in 2020. Two of his research proposals had been successfully selected under MathWorks Excellence in Innovation Scheme 2021. With more than 10 IEEE publications in his career, his current research interests include intelligent design of physical node interaction, deep learning-based design of MIMO communication, and electromagnetic approach towards 6G communication. I welcome Sandeep sir. I welcome you over here.
you so much.
Now the stage is yours. Thank you very much. And I request other presenters, if you are having any question, you may drop here the message after the keynote. Thank you.
Thank you so much, Professor, for your nice introduction. And it's a nice pleasure to be part of this conference. So thank you to the organizing committee for giving me this opportunity. So thank you so much. Yeah. So I share the screen. Hello.
Sandeep sir, with your permission, the recording has also started, I think. Thank you.
Okay. Thank you. So is my screen visible?
Yes, it's
Yes.
visible.
Yes.
Hello. Yeah. Thank you. Yeah. So primarily I will talk about today on the 5G modeling. So I am currently leading the development team in India Networks Signal Processing and Communication Group. So our primary focus is developing a communication system model which includes the both mathematics as well as Maxwellian physics. So I will give an outline where we are actually going towards in future. Some of these snapshots are already available in the commercial website of MathWorks. You can try out in your free time. So I will give some demo also how you can integrate this in using MATLAB for the overall system of the 5G communication, both uplink and downlink thing. So with that, so the brief outline of the presentation is given here. So this is like, first I will talk about why 5G is so much important in our next generation communication systems, and how you can design such a 5G technology using MATLAB toolboxes in a few lines of user-defined codes. You don't have to write down the entire logic or function. There are some customized functions you can directly call and design the system in few lines. And finally, what is the current status in our India scenario, 5G scenario? So why 5G? If you look into the GDP contribution of 5G in any economic system, so it was predicted by consulting agency PwC in 2019-20 range. So US has the highest share, that is around 530 billion, but India is also going towards that level of contribution. If we see in the next, like here, the contribution to the Indian economy is also gradually increasing from the 5G technology. It's going towards 1% of the total GDP by 2030. And this kind of boost is effectively like it's a spreading out of contribution, not just technological. It has other types of subsidiary, like the lower level of ancillary industry will be also influenced by this advantage of the technology. So till date, I think India is around 42 billion. So we have a long journey to reach, because we see it's nearly 10 times US or China is going nearly 5 times than us. So what are the basic difference? Currently we are using 4G, most primarily 4G. There is some 5G introduction couple of months back in India, but it's a very limited city outline. So the major difference with the 4G LTE system and 5G is like, one is definitely the technology used to. So for LTE, we generally use machine type communication for a mobile broadband case. In 5G, there are different alternate technology coming up. One of them is MBB, and the other is previously used MTC with a massive version and some URLLC. What are these technology? I'll show in the next slide. So before going there, the other demand that is coming up as the number of users are going higher and higher, we need a more fast speed of communication. So currently in the latency time for the LTE technology is around 10 milliseconds. That's actually quite efficient LTE technology. In practice, it is much less higher than this. So, but in 5G, it can be less than even 1 millisecond. So that's a huge advantage if we think about a huge number of data points. We think the other major change shifting is in the frequency, because LTE is still now below 6 gigahertz. So if you go for the higher frequency, we will get more number of bandwidths. So that will help us to use, means accommodate more number of user points. That's why 5G is developed in the range of higher frequency. There is a small sub 6 gigahertz band that is currently introduced in India, but you can use also millimeter wave range in the 60 gigahertz range. And the bandwidth spectrum side, like 4G is nearly 20 megahertz, but in 5G times the 4,000. And for actually the 60 gigahertz range, we are actually can accommodate till 400 megahertz. So there are certain physical challenges behind attaining this. First of this, the infrastructure. Like any communication system needs antennas and amplifiers, and all those components are there. all of them should accommodate this kind of bandwidth range at this high frequency. That's a design constant that different industries are investing heavily to develop that technology. The other major difference is the sub-carrier facing in 4G and 5G. Like in 4G, it's always fixed, but there is dynamic characteristics in the 5G technology. That's why that gives a more degrees of freedom in our signal design. Apart from that, how do we allot the frequency? That is quite defined in 5G compared to the 4G. In 4G, we generally use the entire spectrum. There's some advanced technology like WebDM, which is primarily exploited in the 5G range. So we in 5G, we can decompose the bandwidth into different sections. So foundation of 5G performance is can be differentiated in three categories. One is the EMBB, that is enhanced mobile broadband. So which has the advantage of like peak data rate and to means cover a very large area of traffic in the urban, densely populated urban areas. Other thing is network energy efficiency, because nowadays we are going for more number of users means more amount of energy conservation. So energy consumption. So if we can design a system which is much more energy efficient, so if the user number of users changes, we still remain within a certain acceptable energy range. So that's another criteria that is following in this technology spectrum. The other thing is massive machine type communication or MTC. So that has also dealing with local level, like it's you can think about any single office having multiple connection points. So if we how fast we can connect with those office points, that is also kind of connection density. Now this thing actually needs a physical wireline. If we use that has a huge latency backdrop. So if you go for the 5G spectrum like wireless technology, we can reduce that latency periodicity case. That is primarily critical application areas we use. So what are those critical application areas? If we see here, for NS EMBB cases, general objective is to provide as much as wireless coverage in a highly dense area, primarily the industrial belts or the urban areas. For MTC case, it's more like, as I told, that it's a local level. There are two applications. One is high data rate and low energy, because we always want to means reduce the energy consumption in our office spaces. And the other thing is that I was mentioning URL, remotely controlled health surgery. All those needs a very high amount of accuracy. So high amount of accuracy needs a very low amount of latency period. 5G can already some prototypes have been shown that it is successful to provide this kind of behavior. So going ahead, just technology layers, what is the basic difference between the 4G and 5G? So we in 5G, actually this HDP layer is actually a new introduction. Even if we want to connect a 4G layer with the 5G, we need this kind of layer protocol layers. So what are these protocol layers? Some of them are common in 4G also, these RLC and PDCP. So HDFP is nothing but service data adaptation. Like if your network layer actually changes to different configuration, like number of users or number of connection points, how adaptive the total connection layer will change. That's defined by the HDFP. And the other thing is packet data transfer, that is standard for 4G and 5G also. Radio link control, that is how you can control the radio signals between these two different data points. So that has defined layers like ionospheric or tropospheric kind of a channel, which one we use. And finally, the MAC protocol before the physical layer. So that actually controls how user control information are connected to the physical layer. So that is defined by the MAC layer. So as I mentioned that this is a kind of a new addition. So the architecture models to address this HDFP thing. And the other multiplexing and operations like ciphering and encoding things are generally done from this to this layer. And finally, physical layer involves the component interaction things. So let's go by divide this problem into two parts. One is downlink cases and the uplink cases. I'm going for the downlink first. So the signal transfer generally starts from the logical channel, which has some common already used 4G technologies like BCCH or CCCH or PCCH. So those channel information needs to be connected to the transport channel to a particular protocol. So this protocol varies from which we are actually using. So if I go for the BCH thing, then this path needs to be connected with the BCCH or broadcast channel path. Otherwise, there is alternate technique that is called shared channel path that we call SCH. since it's downlink, so we generally call it DLSCH. So the names are quite relatable to the full form. Now, if you add NR before this, what is NR? NR is nothing but new radio 5G technology. So that's a standardized technique. So 3GPP ASN actually come up with a bunch of standards so that we can follow a particular pattern to design these signal waveforms. So for all the MATLAB 5G toolboxes, we use that 3GPP standard 5G NR. So before each code, we just add NR BCH kind of thing. So once we get this downlink controllable channels, then we directly connect. One is if you go for the shared channel, use PDSCH. Otherwise, there is a control channel information which requires a particular downlink control information that is called DCI. So we'll go step by step how these signals can be generated using a 3GPP standard. So first, coming for the broadcast channel. Broadcast channel has already two parts. One is encoding as well as decoding. So you can use NRVCH for particular encoding. If you want to decode this signal, you can just use the decode after VCH. So what does broadcast actually does here? If you can see here, it is nothing but a user equivalent, means it, those encoding part is done by this particular block NRVCH. Similarly, if you want to decode it, you just use this particular thing. There's other thing is also there, that is shared channel decoding and uploading, that is DLSCH. DL is for downlink. And if you want to connect using the shared channel, you have to call the NRDLSCH. So previously in LTE toolbox, you can use DLSCH. For 5G toolbox, you actually need to use NR terms before that. And similar to BCH, you just add decoder to get the decoding performance in the other side. So what are the information or parameters included in this block? You can just type info after that block. That will give you what are the detailed information given inside this block. So next we are going for the physical broadcast channel. So for broadcast channel also we have different variations. The very common one is PBCH, or like a public broadcast channel information, where you can actually based on specify the modulation, which modulation you want to perform to create the data signal, and accordingly you can generate the signal information. For decoding, you just add the decode after PBCH, and that will give you the total thing. If you want more advanced like scrambling sequence or HARQ operation, then you can use this BCH after that PRBS. PRBS is nothing but track type based single scheduling or scrambling. You can use perform. There are a couple of examples you can go with this in the toolbox actually. So other thing is that goes for the broadcast and the shared channel. We have also a bunch of functions. The major two are, one is PDSCH and the other one is PDSCH RBS. So RBS means includes the cabling behavior. If you don't want this, you can go for the default thing like this. What are the configuration parameters? So indices, you can manually just investigate and change those parameters based on the requirement of the 5G layer mapping. So we'll show one use case, practical design, system design in the next some of the slides. So the next we show that if you are using actually control channel information, you need the UCI or DCI information. So where does that come from? That control signal is coming from a particular block that is called control channel block. So for that also there is a couple of functions are available. All these functions are actually written based on 3GPP standard. So you don't have to worry about manually writing or anything. Just call this block, mention the number of nodes and number of modulation types, and it will generate you the standardized symbol output. So for this also you can just, there is a of both encoding, you can go like this way, and for scrambling you just add the PRBS after that. To visualize those things, you can call the config or space parameters, which will show what are the details actually inside it. And there is another modification generally used that is called control resource setting. So for that case, we have a separate block called the port set block. Port set configuration, using this, you can just manually modify what are the parameters inside it. So once we get this control information, we can now connect with the physical channel using this particular block with PDSCH. Now there is one more parameter, like carrier information includes the frequency information as well as signal types. So for that case, we have a block called inner carrier configuration. It is quite quite common both in uplink and downlink cases. You can use this to control the carrier frequency and type of signals that you want to specify. And similarly, the resource grid, we know that 5G architecture little is different from LTE. We have a user plane as a resource plane. So for that case, to design the resource grid, like a rectangular resource grid you want to design, so that can be done using this inner resource grid. These things are quite common for downlink and uplink, so you can enhance in both the places then. There is other part, like before generating the control information, we generally do some kind of channel coding, like LDPC coding or polar coding kind of a thing. So there is a very compact block that is called NRDCI encode, which includes polar encoding inherently. So if you don't want to use the polar encoding, you can change going inside it to change the encoding type to LDPC encoding. So that can be done. So what is inside this block? There is two is possible, as I show here. So either you can use a directly NRDCI encode block, that's a complex block of 3 operations, or you can manually use the different rate matching polar encoding. Those 3 blocks can be connected and just perform the overall performance. So once you get the encoding part, then you go to the physical layer, that is PDSCCH control channel, physical downlink channel, and you can just modulate the symboling based on your required symbol rate and then connect to the channel. The channel is considered shown here is AWGN, but you can choose any other channel as per your requirement. So this is the upper part, that is modulating part. If similarly you have to perform the demodulation, that is also similar behavior. So instead of that, the sequence of operations is followed. Here we have the recovering the following towards the CRC decoding part. It's actually successive decancellation decoding part. But you can manually control it choosing other advanced decoding part. That's also flexible. So now if you want to just design this system, let's say one example or something like that, that we are going to show in the next, how you can actually design this whole entire block here. Yeah. So whatever the figure that I shown in the previous slide, same here. So I want to design such a downlink control initiation parameter. So design of 5G control information, you need the message bit as well as the number of coding bits. So this is your coding bit, E, K is 64. Your total message length, we are just considering 288. So your code rate will be K by E, that will give you the code rate. Similarly, the integration points, we are considering 100, you can change it to any numbers. And the scambling ID, we are just considering 23 based on the 3GPP values. So next level, you have to perform this encoding part. So we are direct and passing this information inside it. So we have a random information of K bits already constructed. You can change the data type to other also, that's also flexible. And based on the message length, you can actually specify the E here, and it will create a decimal length, that is the length dimension of E. So that is your total encoded signal length. So once the encoding part DCI your control information encoding is done, you have to connect it to the next CCH. CCH for control channel. For other case, we have PD, SCH and other things. But for this case, we are just calling PDCCH along with this generated encoding signal, DCI HCW, and pass the overall specification of the 5G channel, that is RNTI NID, and that will give you the ultimate symbol information after the channel coding. And then we just connect this symbol to the AWGL channel, which are just assuming a random AWGL channel with particular SNR values and system symbol information. Symbol information coming from PDCCH, and it will just give you what will be the finally transmitted signal to that particular channel, RX SIM. So this completes the transmission side. Now from the reception side, you have to decode this signal again. So based on the received signal RX SIM, and you know the channel information is known to you, and you just specify the channel variance, that will give us the final decoding signal. And once the channel decoding is done, then you have to decode the control signal also. For this case, we are just calling the DCI decode part here. So it's quite complementary with the encoding part. So using this way, now you can compare how accurate your results are. You can just call is equal between the transmitted and finally decoded bits. That will give you a measurement of the accuracy, how good the algorithm looks like. So next, going for the physical signals. So till now we are up to the control signal. For physical signal, can be different types of synchronization, like PSS or SSS blocks. Generally, other cases we have different PTRs. So whichever physical signal you are using, based on that you are actually choose the reference signal. And this is the library generally that downlink synchronized signals or other things generally used for to measure the quality of the signal for the user document towards the base station. For the other case like reference signal, we also have this library like PDSCRS, and for demodulation purpose you can use the PBCH instead of PDSCH case. And for channel state, there is a CSIRS block is already available, so you can use it in terms of NR standard. And for phase tracking part, that's a little advanced thing we generally use to track based on the polarization of the signal. So to detect the polarization, we can use the phase tracking reference signal, that is PDSH PTRS thing. PTRS stands for the phase tracking reference signal. And all these signals are similar to the previous case. So you can just decode this using the other decoding blocks. And reference signal, we have a NRPRS, and for carrier signal, it's same as we are showing before. And finally, the usefulness is like it just carries the information, channel state information from the different measuring of a real-time system, how the non-ideality or how the error blocks are actually affected based on this particular defined standard signals. We can actually measure it based on different channel state information. So channel state information is generally controlled by CSRS block, or you can modify it using the channel block used in the, for this our previous example we used, let's say AWGL, but you can give it any other random channel and just measure the performance behavior in different scenarios. So next we are just going for the uplink cases. So uplink is also similar to a dial link, but the flow of information little bit different. So here the channel information are CCCH or DTCH, we generally call it. And since it is uplink, we are just instead of DL, we are just calling it ULSCH. So ULSCH is also provided in LTE, but for 5G we'll add NR before this. That will give us the total uplink for the particular 3GPP 5G layer. And the other is like for connecting it to the physical layer, there are two ways. One is directly shared channel, that is PUSCH. But if you want to connect it to control information, you need to call the PUCCH. CCH is for channel control channel cases, and SCH for shared channel cases. If you use the control channel case, then you need a control information. So control information comes from uplink control information UCI. Previously it was DCI for the downlink cases. And if you go for the RSCH cases, then you have a physical layer block called PRSH or track block. Now, how can you utilize those for different purpose? So for encoding purpose, we have a similar block, that is NRULSCH. To decode it, we just add the decoder block after that. If you go for more advanced thing, like you have a multiple channel, you want to multiplex them. So there is a ULSCH shared channel multiplexing operation is there. So if you add in the transmit side this particular multiplexing block, similarly you have to do the complementary operation in the receive side. That's why demultiplex blocks is introduced here. So the information of these particular blocks can be configured based on info and config clause. So that's why till now it is lying like quite similar with the LTE, but you are just adding NR before them. So to encode this uplink signal, similar information is it can be done through encoding block. So we have a performance parameter called NR UCI encode, where you can specify polar encoding or LDPC encoding, whatever you are requiring. So there, based on this thing, we have actually come up with nearly 5 or 6 variations for the physical layer uplink channel. So whatever information we need, based on that, we can just modify the calls. So default call is generally PDCCI1. So that is 4 to 15 level. You have to accordingly change the block numbers, which one you are actually calling for it. So the other information is there is that PRSH. So not always we actually go for the CCH format. So sometimes we need the PRAC symbols to be accessed to a random channel. So in that case, you can use the PRAC version to use for this case. There is certain modulation flexibility is also inside these 4 blocks only. You can change the modulation from QPSK to other thing like BPSK or 16 coarm case also supported here. So those things can be explored for different further future applications. Here is a library, total library, what is actually given in the shared channel case. PUSCH for the default case. And if you want to modify it, you have to go inside it and change the properties based on your requirement. Similarly, if you want to design a particular scrambling case, you just need the PUSCH. After that, you need a scramble block that will do the scrambling side in the transmission block. If you want to do the decast scrambling in the reception side, you have to add this similar block in the here. The other thing is DMRS thing, similar to the uplink case, you can use PUSCH DMRS here also. So difference is between the up and down is only one letter, that is PU instead of PG we are using. And TRS block is also supported here. And finally, the codebook design that you can do using PUSCH codebook of that will give you the total means uplink codebook design blocks, whatever is required. So inside PUCCH, as I mentioned, if you call directly PUCCH, I think it is default is PUCCH1. But if you change it to other also, you can manually do it. That is possible. Now inside each block, again, one more nested layer you can modify, that is called PUCCH config layer. So based on that, you can just change your actual uplink signal information based on the requirement. Part of the random access channel, the default one is PRAC or PRAC we call NRPRAC, but you can change its underneath modulation behavior or the coding behavior. That is using the prcch.properties you can use to change the defined parameters there. For modulation, demodulation, you can definitely use a modulate or demodulate block to change the output WebDM signal waveform. So how does it look generally? To give a feel, like if you have a nearly 140 symbols and you have a different subcarriers in different range, your default PRAC symbol looks like this. So you can change the number of symbols or number of subcarriers to get a defined waveform frame, whatever is required. And finally, the reference signals is also same, just a little difference, that is PUSCH here instead of PDSCH. And DMRS are also quite similar to the previous. So it's quite a useful, because once you know the block of operation, you can just manually change uplink to downlink and design the overall system blocks. For TRS also, here also we just provide a PTRS block for nonlinear cases, specifically for polarized communication. You can use this block for defined phase information tracking. And for reference signals, like in channel sounding and other cases, we have a default block that is called NRSRS that goes for the just generates the reference signal for channel sound. You can configure it based on your requirement like this way in our SRS config. So these are all the overall system design you can just perform using couple of blocks. So you don't write down the entire codes or anything. This is the general outline, how the overall system looks like. So first you actually define what are the higher layers you require to design. So based on defined blocks, you can just define the multiplexing or as well as the channel type, like it's a broadcast channel or shared channel. And based on the modulation, you can generate the data symbol. Now to connect that data symbol, you can just call the physical layer blocks that we saw, like PBSCH or PDSCH thing, and then just final output you can just visualize using our channel modules. So channel modules can be defined AWGN or relay or fading. Different fading channels are also supported. You can choose and modify the properties, and you visualize the final output here. So this is the total workflow, and I'll just give another shortcut how to generate the waveform instead of writing any codes. You can just, this is the final workflow. Like you have to first step of a design process is creating a 5G waveform. Then change the parameter and finally generate the waveforms. Once you generate the waveform, you can export it into your favorable format, like any file formats, or in your command line also you can export it. So we have a default app actually that is called 5G waveform generator app. So if you go for the open the MATLAB, go to the apps, there is a 5G waveform generator. You click on this thing, it will give you different types of whatever the channel that I talked about previously. Those options are given here. So you choose for this case, let's say you choose a downlink thing. So underneath the downlink thing, you can see multiple variation, whatever you need require actually. So once you choose that, let's say one particular block, you get a PDSH block. So here actually you can change whatever you need, like you can change the modulation as far as your requirement. Once you are done with all these things, you can export this waveform in the form either to your command line workflow or to a Simulink workflow, whichever you are comfortable with. And with that particular standard 5G waveform, you can then perform your other operations based on the requirements. And you can visualize this whole channel information also using our spectrum analyzer. This is the resource grid block. The waveform can be clicked on this. If you click on the spectrum analyzer, it will give you the Fourier spectrum of that particular signals. And you can just, as I mentioned, that you can just modify whatever the encoding part or anything you want to modify, that can be done here manually. So one major example that I would like to show is like, if you have the carrier information, how you can actually map this to the 5G resource grid. So for that case, first you have to define what are your carrier configuration is, and you have to define what is your transmit antenna configuration also. By default, we generally took one antenna, but you can change it to 4 or something else also. So next, once you specify your channel configuration, Fourier configuration, and the number of transmitter antennas, just call the PDSH block. So here you can just configure the whatever the information inside it. So that will like modulation. I am going for QPSK to 16 comm here. And number of layers, number of 5G layers that you can modify to whatever numbers. Just for simulation purpose, we have done it to. You can change it to anything. If you want to do more advanced technique, like you want to actually utilize the entire carrier broadband spectrum, you can just set this PRV set to this type of range based on the grid size. And to visualize what are the parameters that is lying inside it, you can visualize it like this way. Change the RNTI or PTRS, whatever is you feel comfortable with. And based on that, you get the entire PDSH symbol. Now you can use this to any Simulink model or anywhere and perform your next level of operation in the that will depend on the application that we want to go into. And let's say we are actually done with the PDSA generation. Now we want to get into the shared channel level. So to generate the shared channel, we are just calling the NRPDSCH here, passing the carrier information and previously generated PDSCH configuration. And we are just mentioning which are the number of bits, shared channel bits that is required. And based on this information, it will give you the number resource. So what are the steps involved here? First, it generates the PDSH information in the previous cases. Next, it connects those symbols to the based on the standard information. So standard information needs both PDSH as well as the carrier information here. And it finally generates the code words based on your PDSH bits. So all this information can be just like, since we have given number of layers 2, so our information is 8112 cross 2. So you can change it to any number of layers and get according information. So then if you go for further, like you want to connect DMRS modulation there, so that is also can be possible. Just call PDSCH DMRS, pass the PDSCH symbol and carrier symbol. It will generate you the DMRS version of PDSCH. And if you want to visualize how it looks like, so that is also doable. Like here, if you just default PDSCH without DMRS and with DMRS, you can visualize the number of symbols versus quadrature amplitude that can be done here. So plotting, just use the standard MATLAB plot command, it will give you these plots. And then finally, visualize the spectrum, how it looks like. So based excitation of those antenna layers will be there. So here you can do more advanced operation, like you can include the electromagnetics here, how the based on the Maxwellian physics, what will be the weighting numbers or the excitation coefficient that you can do, and that will include the coupling information if you just do more advanced level here. And based on this excitation, that coefficients of the antenna layers, we can define the precoding weights here. And this precoding weights is actually nothing but your layer number. Based on the number of layers, it is actually maps it inside the PDSH block. And then you just, for each number of layer, we have a setup of the symbol of PDSH. We just multiply to each map, means each layer of the resource grid, and that will generate your final pre-coded versions. So since the dimension we can see here, it is just crossing, it's as a transpose operation. That's the total symbol rate versus the number of antennas we are getting here. So this can be done just using code version here. So you get the PDSH for each layer, multiply with the weighting coefficients, and just assign it calling the function called resource grid. Since we are using NR new radio 5G layer, we are just calling NR layer here. And that will give you the final symbol for each stacked layer in the resource grid. Now let's say we want to visualize only one antenna in one particular layer. That is also doable. So if you just specify the number of antennas or number of layer indexes, that can be extracted. But there is a standard command also that you can do through code line, that is extract resources. You can get the exact information which you want to plot. So get the total indices and pass the grid information. And based on your index number, you can just extract the particular layer indices, what are the precoded symbols. So it looks like visualization side, you can do this thing. I like to plot the first antenna, so I'm putting it one here. We have 4 antennas, you can put any one of them. And this will give you the how the actually resource grid information looks like this. So since we are using default OFDM symbols, so it is just OFDM modulated signal in the entire resource grid. And based on like this grid size or like any number of antennas, you can play around how the other things like coupling and everything is actually changing this behavior, the waveform that can be investigated further thing. So this is the code actually that were used for internally perform based on the extracted information. So for each indices we extract the information, then we are performing the MRS block here. So that is doing the multiplication based on the antenna weighting coefficients. Sorry. And for each antenna block, we can also visualize the DMRS symbols. Previously without DMRS, so now this is with DMRS, the slight change. And for MIMO decoding, you can also visualize the signal blocks like this. So based on the signal strength, you can place the antenna where you want to place it. And finally, for performing the OFDM modulation, we have a direct block that NR OFDM modulate. You can just pass the PDSH information and the carrier signal. It will perform the OFDM modulation. This is the spectrum that looks like in the time domain. So based on your requirement, you can optimize this spectrum in both time domain as well as the frequency domain to the overall 5G information. So next one is polar encoding that we saw. This is kind of a individual block performance. You can do it, or you can do it separate block also. This is the kind of a behavior that we showcase for defined CRC. We have also LDPC encoding block that you can use instead of polar encoding. And there is some practical implementation based on these toolboxes actually. One interesting block is like it's a 64x1 fully implemented version of the 5G terminal by defined industry interdigital. They have fabricated it and standardized it also. Very successfully validated based on a certain parameters. Like we are receiving gain almost nearly above 70 dB. Our standard antenna gains is within 10 dB generally. So that's a huge potential and also physically validated. And from both sides, actually, we see that 5G growth is very low till date, even because it's nearly 14%. Because main challenge is in the physical block. Your physical component needs to be actually prototyped. Otherwise, theoretically, it cannot be validated in practice. So there is certain scope of research, I think, available till now to develop 5G blocks. Starting from healthcare to automotive, we have still open market. We can work on these domains. Potential size also India is still low. We have to go into a certain level of acceptable of increase. Scope is there. Defined kind of manufacturing industry or smart utilities also India is still quite low, less than $20 billion. So we can improve those kind of application areas and focus on this. Similarly, for the manufacturing sales also we are quite low. And we have actually introduced 5G last month, I think, last 1st August actually, not last month. So there is the spectrum majorly by Reliance, but major challenge is that Indian 4G operator infrastructure needs to be thoroughly changed if we go for the 5G. So what that is an expensive operation. So the cellular organizations are a little bit skeptical to implement 5G in a broad range. So they are coming up with different solution. One is the frequency range. They want to reuse the 4G frequency range for 5G infrastructure. That's a challenging in terms of the logic that it works. So what people IIT Hyderabad and IIT Chennai come up with some Indian version of 5G that is called, they are calling it 5GI, which major advantage is for the rural areas, which does not have the 4G till now always. So they are covering 5G for the rural as well as the urban areas, but that needs a science. So things of research works actually pending in this domain also. Anyone can perform on this. So that's pretty much I have. Thank you, and sorry for some.
Thank you.
you.
Monidipa ma'am, over to you, please. Thank you.
Yeah, thank you, Dr. Ghoshal, for the interesting talk. We have some more time, so I think we can take a few questions. I think 2-3 questions. If anybody has any queries, we can ask Dr. Ghoshal. Audience. So if you're planning on implementing anything, you can ask him.
So one more thing I would like to open up for this.
Okay, I have a query, Dr. Ghoshal.
Yeah.
It was a very nice talk you have delivered related to 5G and how the researcher can work on it using the MATLAB tools. So I have a general query, basically that general awareness related to 5G and its security aspect. How you have look about the security aspect in 5G in comparison to 4G?
Yeah, so 5G has I mean, one of the slide I mentioned that it has a degrees of freedom relatively higher than 4G because it uses phase tracking information as well as the polarization information of the signals. So based on each user, you can encode the signal means specific to the particular user. So that gives a higher amount of encryption, means higher amount of security aspects. So that's kind of an advantage compared to the 4G to 5G.
Then second is related to the base station. You have mentioned that the base station need to be changed completely when we have to change to 5G. And you also suggested that Indian version of that 5GI or what you have mentioned, proposed by IIT Madras or IIT Hyderabad, exactly. So actually, how much, whatever the changes they have proposed in comparison to the existing technology, is the same way or there is some new proposal or new ideas incorporated in that, so that with low infrastructure changes that can be supported?
So standard 5G models, we know that it is developed by Huawei or Samsung or whatever, or any wireless communication group. So those are based on their path model or propagation model. Everything is stochastic, and those are based on urban data only. But Indian rural scenario is not that much densely populated. So that model does not actually work that accurately. Even if you have the hardware, that the theoretical models or the architecture will not work in the rural areas that efficiently. So that with that perspective, they have come up with different path loss model and propagation model. Similarly, they want to use the existing 4G at certain amount, so that we need minimum change when we go from the 4G to the 5G. Because no company will want to invest large in the rural areas from cost-effective side. So they have to come up with alternate technologies slightly different from the conventional 5G thing.
Another is that it may be my last query. That we have just few days or few months back, we have a public litigation conflict or appeal is filed in Supreme Court of India related to the hazards, health hazards associated with the 5G. So I think you are the right person to tell how much it affect the your society or public life like that.
So if you think about like I see lots of things, but I think TGP community or the wireless community in the outside world, they have come up with actual experimental outputs that it actually very minimal effect. This is in the nanowatt or milliwatt range of power that got transmitted. Even that milliwatt power that is being transmitted, very one fraction of that milliwatt power is actually absorbed in our biological cells. So from the point of physics, that does not seems to be that much significant. But definitely, if you have a very high density 5G signal focused on a small area, it will definitely have
Okay, I got it. Thank you, Professor Ghoshal, for it.
Yeah, thank you.
Thank you, Niranjan sir. Anybody else from the audience who would like to? Okay.
So sorry, I'd like to mention one thing. We have released a couple of open source projects for the students in MATLAB GitHub page related to 5G and other technology. So if any student community is interested, they can participate it, they can get certificates and other things. That's a problem for them.
Okay, yeah, that will be very helpful. So all those final year students or who are looking for projects or summer training and all those things, so they can contact Dr. Ghoshal, and otherwise anybody from the CINE organizing committee, so they can help you get in touch with him in case you have any other semesters also, third semester, fifth semesters. So with senior students, you can,
it's open to everyone.
So anybody else who is here? So I'd like to extend our warmest thanks to Dr. Sandeep Ghoshal for taking time out from his busy schedule to join us for his talk. And I think all of the students and all the listeners and faculty and all of us were really interested and enlightened by his talk. And I think you've given us a lot of research directions to look forward to. So I'll hand it over to Trishani. Trishani, you can take over.
Thank you.
Yes, ma'am. Thank you so much. Thank you so much, Dr. Sandeep Ghoshal, sir, for such an interesting presentation. And I would like to thank our keynote session chairs, Dr. Tanupriya Chaudhary, sir, Dr. Professor Monitipa Roy, ma'am, Professor Niranjan Roy, sir, for chairing this session. And now I would like to ask all our authors who have a presentation today to join their respective
sorry for
track
interruption, Trishani.
Yes,
I
sir.
kindly request you all to please switch on their video so that we can have one photograph. That's it.
Sure, sir.
Thank you. I kindly request all of you, please switch on your video so that we can take a photo. Trishani, I request please take a screenshot, please. Thank you.
Sure, sir. 1 minute.
Usually take a screenshot, print screen.
Yes, sir.
So this is Dr. Rajiv Chatterjee, co-founder and organizing chair of CINE 2022. From my side, I thank you all the session chairs and also our eminent speaker, Dr. Ghoshal. Thank you for your valuable time and also the time given by our chair, Tanupriya Chaudhary, Niranjan Ray sir, Monitipa Roy sir, madam, and also Hafizul. Thank you. And again, after this, we have a track. So I request all the participants, their authors, please move to your respective tracks, track 1, track 2 of day 3, and our session chairs will be there. And again, at the end, day 3, 4 to 5, we have a very nice and interesting talk by Professor Min Zhu from Carnegie Mellon University. That will be again online. And so I again request all the authors, even if all these presentation part is over, please join us in the last talk. Thank you. Thank you all.
Thank you.
Thank you. Bye.
Thank you so much.